Okay, so in the last part of this chapter, we are going to look at dynamic indexing. Up till now, we have assumed that our corpus or collection of documents is static, right? So we are not assuming that the corpus is dynamically changing. But if you look at web search engines, the web corpus is not a static corpus, it's continuously changing, right? There are documents that are being added to the web all the time. There are documents that are being modified. There are documents that are being deleted. So what happens when documents are added, modified, or deleted? If those additions, modifications and deletions were immediately reflected in the inverted index, if we had to immediately reflect them in the inverted index, then we would need to add uh, terms to the postings list and perhaps to the dictionary also. If we encounter a brand new term in a document that's added, we could be modifying entries in the postings list, and we could be deleting entries from the postings list and sometimes from the dictionary, right? So how do you manage these scenarios where the documents are continuously being modified and those modifications need to be reflected in your inverted index? That's what we're going to look at in dynamic indexing. The simplest possible approach that you can think of is to maintain a large index, which we will call the big index or the main index, and then any new documents that are appearing in the corpus will go into a second auxiliary index, and this auxiliary index is going to be small. In fact, we can assume that it's so small that it can be entirely maintained in the RAM. And what we will do is, when a query comes, we will try to answer that query by sending it both to the larger index and also to the auxiliary index. And we'll take the results from both the indices and combine them. How do we combine them? We'll take the OR, because the auxiliary index is maintaining an index on documents that are not in the main index. The auxiliary index is maintaining an index on the newly appearing documents. So we'll need to combine, we'll need to take the OR of the results in both indices and then serve them to the user. So that's what we will do when we are looking at insertions. Okay, so when a document is inserted, we'll insert it into the auxiliary index. What about deletions? The way we can handle deletions, the simplest way in which we can handle deletions is to maintain a bit vector for deleted documents. So this bit vector will indicate which documents have been deleted. So when a particular document is deleted from the corpus, we won't actually delete the postings list entries for that document in the index. We will just mark that document as deleted in the bit vector that we are maintaining for all documents. What will be the size of this bit vector? The number of documents in the corpus. Now when a query is answered, we will take the list of documents in the result. And it's possible that some of those documents may have already been deleted. But because we didn't delete those documents physically from the index, the results may contain those doc IDs. So we will then take the bit vector, the invalidation bit vector, and filter out those documents in the result which have been marked as deleted in the bit vector. That's how we will handle deletions. And then substitutions or modifications can be handled as a sequence of a deletion operation followed by an insertion. Right? Any substitution operation can be treated as a deletion followed by the insertion of a new document with those modifications. Now, as the auxiliary index grows, which it will, especially if you are talking about a web corpus, there are new documents appearing on the web all the time. At some stage, this auxiliary index is going to be too large for it to fit into main memory. In that case, we will take that index and then merge it with the main index. How do we merge two indices? We just discussed that in the last class. Right? We'll use some kind of we'll use this merge algorithm that we talked about when we discussed external sorting to merge both indices into a larger index. What will be the time complexity of that uh, merge algorithm? Well, we'll need to read the entire main index. We'll need to parse the entire main index and merge every postings list in it with the postings list in the auxiliary index. Okay, and this will be an actual merge operation. We'll be merging the two lists. We won't be, in some ways you can say we'll be taking the OR of both the lists, right? And then we'll have a single index, which is a big index at the end, which will store back into the onto the disk. By the way, when thinking about dynamic indexing, forget about uh, cases where the index is distributed across multiple machines, right? So in the first part of this lecture, we talked about distributed indexing. But just to keep things simple, don't think of dynamic indexing on a distributed index. Okay, let's not bring both those things together at the same time. Let's just think about dynamic indexing, assuming that the index is residing on a single machine, and then you can extend that to a distributed index. Now the problem with this simple approach that we saw for merging this main index with an auxiliary index is that every time the auxiliary index grows in size, which it will pretty rapidly if you're talking about the web, you'll be doing these constant merge operations on the big index, right? And since this merge operation is expensive, uh, while you're doing this merge, your index will not be serving any useful results, right? So the performance of the system on queries will be poor because the system will be busy doing these merges so often. And then we also have to think about what exactly we mean by merging. One possible scenario is to think of, actually merging the postings lists as I just described. The other option is to to take the postings list for a particular term in the main index and then link it. So here's what I'm talking about. In your dictionary, you'll have pointers to the postings lists. One scenario is when you maintain each postings list as a separate file. The other scenario is when you maintain all these postings lists together as a single file. So if you maintain the whole thing as a separate file for each postings list, then merging can be efficient. Why? Because you can just take the postings list for a particular file, merge it with the postings list for the same term in the auxiliary index, and then create a new file. But the problem with maintaining postings lists for each term separately is that the number of files you'll have will be equal to the number of terms in the dictionary. And if you have so many files, then your operating system becomes very slow. Right? I don't know if you've noticed that, but if you have too many small files on your even your desktop machine, your machine tends to become slow. I don't know if you've noticed, if you have too many files stored on your desktop, have you noticed that your machine may appear to be running slower than if you have a fewer number of large files. So which is why in reality, uh, the index is usually treated as one big file or at most a few files, not a huge number of small files. So regardless of how you store it, you will still need to do this merge operation, which is going to be expensive because you'll need to touch every file. Even if you have a few files stored, you will still need to read that whole file, read the contents of those files while doing this merge operation.